Okay, shall we get started then, if everyone's got the notes? So last week we did Cournot and Bertrand a bit more properly than you'd seen it before. Okay, but we ignored the question of whether or not firms would ever want to enter these industries in the first place. So, remember with asymmetric marginal costs, Bertrand, you got this strange thing where all the firms with high marginal costs just weren't producing anything at all. So you wonder why they would bother entering the industry in the first place. Okay, so that's what we're going to be looking at today. We're going to be looking at entry decisions, and we're also going to be looking at the relationship between Bertrand and Cournot, and what you can say about which is the more reasonable model of competition. Okay, so brief outline. We're going to do a bit more game theory to start. And I've got £10 worth of 20p coins here. So you'll again have another opportunity to rob me blind. So some of you got some money off me during micro, I guess. So you can do it again. And then, so we'll remind you of a bit of game theory, and then we'll go on with static oligopoly. Entry, welfare's like under Cournot and Bertrand, whether there's too much entry or too little, and whether we can say anything reasonable about the Cournot versus Bertrand. Notes are in a box. So, have you seen sequential games, extensive form games before? Hopefully you have. So this is just a reminder. Okay. So this is just a game that I stole off Wikipedia. It's not a particularly interesting game, but it illustrates the concepts of subgame perfect Nash equilibrium. Okay, so there are two players in this game. Player 1 gets to choose first, so he interestingly gets to choose left or right. Player 2 then gets to choose K or U. Okay? The payoffs are given along the bottom. Okay, so 3-1 means that if you get to this point, player 1 gets 3, player 2 gets 1. Okay, here player 1 gets 1, player 2 gets 3, player 1 gets 2, player 2 gets 1, both of them get nothing. Okay, so it's a sequential move game with player 1 going first. So player 1 goes left, then depending on what choice player 2 makes, you can get to this world or this world. If player 1 goes right, then depending on what choice player 2 makes, you get to this world or that world. Okay? So let's just imagine we were here to start with. So imagine player 1 had already played left. What would player 2 want to do now? U. Exactly, because 3 is bigger than 1. Player 2 always prefers to do U. And likewise, if we were here, what would player 2 like to do? Okay, yeah, because 1 is bigger than 0. Okay. So, given that player 1 knows that if player 1 plays L, right, player 2 is then going to play U, that's what you just said. And if player 1 plays R, player 2 is then going to play K. Which of L or R is player 1 going to want to choose? R, exactly. Because if player 1 plays R, then he gets 2 rather than 1. Okay, player 1 realizes that player 2 is going to play in this certain way. Okay, so if player 1, player 1 would like to get this outcome, maybe, but they know that if they play L, they're not going to get that outcome, they're going to get that outcome. Okay, so there's no point in player 1 playing L, because if they play L, they're going to end up with 1, whereas if they play R, they're going to end up with 2. So that's the subgame perfect Nash equilibrium of this game. All it means to be subgame perfect is that at each node in the game tree, it's like you're looking at the Nash equilibrium from that point forward. Okay, so it doesn't matter where you are in the game tree, everyone's playing the Nash equilibrium at that point in the game tree. Okay, here, at this point in the game tree, there's only one player moving, so it's kind of a one-player game. So playing the Nash equilibrium just means at each point in the game tree, each person is choosing what's best for them. Okay? But if you look at this graph, you'll see there are some this picture, you'll see there are some extra lines marked. Okay, so the red thing is the subgame perfect Nash equilibrium. That's what we said. So here the red mark is showing you playing U there, it's showing you to play K there, and it's showing that in the subgame perfect Nash equilibrium, player 1 plays R. Okay, but there are also these blue lines. Can anyone explain what the blue lines might be saying? No one wants to go? Well, okay, so imagine you're player 2, okay? Rather than playing this game, player 2 is going to end up with 1, right? That's the outcome of the subgame perfect Nash equilibrium. Whereas maybe they'd prefer to end up with 3. Okay, so imagine you're player 2 and you think, I know what I'm going to do. I'm going to program a robot to play on my behalf. Okay, so you program a robot that looks at what player 1 does and acts a certain way given how player 1 is acting. Okay, so you decide how to program this robot at the same time as player 1 is deciding how to play initially. Okay, so player 1 is still going to choose L versus R, but you're going to kind of choose the program for this robot. Okay, so you're going to say, if player 1 plays L, I want to play either K or U. If player 1 plays R, I want to play K or U. Okay, and the important thing is that because you're giving this power to the robot, you're committing to what you're going to do. Okay, so you give the robot the power to play on your behalf, and that way, you can't change your mind about what you're going to do in the future. Okay, so then we can represent your strategy like this. So KK means play K if player 1 plays L, and K if player 1 plays R. KU means K in the first case, U in the second case. UU means U in both cases. Okay? This one means U if player 1 plays L, K if player 1 plays R. Okay, so rather than thinking that now as a sequential move game, we can also analyse it as a simultaneous move game, where, rather than choosing what to do, player 2 is kind of choosing the program for this robot. Okay, they're choosing what to tell the robot to do. And then this now looks just like a normal 2-player game. Okay, these are the actions of player 2, these are the actions of player 1. And you can go through the game to find which the best responses are. Okay, so the best responses here are underlined. And it's easy to see that we're now 2 Nash equilibrium in this game. So here's what we were looking at before. It's 2-1. Okay, if he's playing UK and player 2 is playing this thing, UK, and player 1 is playing R, then neither of them want to deviate, right? Because if player 2 deviates, given player 1 is playing R, player 2 can't do better than 1. 1 is the best they can get, so player 2 doesn't want to deviate here. And likewise, player 1, well, they get 2 here, they'd get 1 there, so player 1 doesn't want to deviate either. Okay, so this is a Nash equilibrium of a simultaneous game, but this is also a Nash equilibrium of a simultaneous game. What's happening here? Well, if you were player 2, here you're getting 3. You can't beat 3, so you don't want to deviate. Player 1, he's getting 1. If he deviates to R, he's getting nothing, so he doesn't want to deviate either. So in this simultaneous move game, there are 2 Nash equilibrium. Okay, but only one of them is what we call subgame perfect. What's happening is that if you can program a robot like this, you can commit to do something crazy off the equilibrium path. Okay, so what's happening in this UU equilibrium is player 2 is saying, doesn't matter what you do, I'm going to play you. Okay, so player 2 is committing to do something really stupid in this state of the world. Okay? So player 2 is saying, even if you play R, I'm going to play you. And doing that is enough to persuade player 1 to play L in the first place. Okay, so the Nash equilibrium of these games also feature these equilibria in which people make crazy commitments to do things off the equilibrium path. Okay, so we don't like this equilibrium. I'm not saying this is how we should go about solving these games, but it's important to see what subgame perfect Nash equilibria are ruling out. Okay, so these are the two Nash equilibrium of the game, but the original, the sensible one is this subgame perfect Nash equilibrium in which players can't promise to do something crazy off the equilibrium path. Okay, in the subgame perfect Nash equilibrium, at each point in the game tree, player 2 is doing something sensible. Okay, whereas in the Nash equilibrium, this other equilibrium, at this point in the game tree, player 2 is promising to do something crazy. Okay, so when you're solving for subgame perfect Nash equilibria, you have to, imagine everything that could possibly happen, even if you think it never will happen, and you still have to check that people are behaving sensibly in that outcome. Okay, so if you played this game, right? You end up here. Player 1 always plays R, so you might think it wouldn't make any difference what player 2 was going to do in this state of the world. Okay, but what people are going to do in other states of the world that never happen can actually have an impact on how these games play out. Okay. I probably thoroughly confused you. The important thing to remember is that you always solve these games backwards. Okay, so you start at the terminal nodes. Okay, you consider every possible terminal node, and you solve the game in that last period. Okay, and then you go to a period before, and you solve the game. Then you go to the period before. And that way, people can never promise to do something crazy off the equilibrium path, which is what's happening. Okay. Do you broadly understand the difference between these two types of equilibrium? Yeah, sure. So what's happening here is we're imagining that the player 2 could somehow commit to following this strategy. Okay, so player 2 makes a commitment at the same time as player 1 is making their decision about what they're going to do, depending on what player 1 will do. Okay, so if they choose to play this strategy, they're committing to play K no matter what player 1 does. If they choose to play this strategy, they're committing to play U no matter what player 1 does. And here they're committing to play K if player 1 plays L, and U if player 1 plays R, etc., etc. Okay, so we're just imagining that somehow player 2 can make these commitments. Okay, so you can think of a robot that's playing for them if you like, or maybe there's a legal system or something. Okay, so if player 2 can make these commitments, then it looks like a simultaneous move game now, right? Player 1 is choosing L or R, player 2 is choosing what commitments to make. Okay? So then each of these cells is going to give us the payoffs just like in a standard two-player game. Okay, the first number is the payoff to the row player, the second number is the payoff to the column player. And what we were saying was that these two things were Nash equilibrium, and the way you check is you just check that neither player wants to deviate in either case. Okay, so here the row player, okay, he's choosing between L or R. So given the column player is committing to this, okay, they're committing to play U if they play L and K if they play R. Their choice is between 2 and 1. Okay, so the row player here would always prefer 2 rather than 1. Okay, so they want to play R. Likewise, the column player, given that the row player is playing R, they've got a choice of 1, 0, 0, or 1. Okay, and 1 is weakly better than all of them, so they're happy to play 1, then they deviate. Okay, and you can do exactly the same thing here. So what we're saying is that when players can make these commitments, okay, to actions later on in the game tree, then we're extra equilibria of these games. Okay, so these two things are both Nash equilibria, but the one we like, the sensible one, is what we call a sub-game perfect Nash equilibrium, because at each sub-game of the original game, people are still playing the Nash equilibrium. So, you know, you can think of this as being a sub-game, okay, and in this sub-game, player 2 always wants to play you, that's fine, but this is also a sub-game, okay, and in this sub-game, player 2 strictly prefers K to U, because if we play K they get 1, if we play U they get nothing. Okay? So, in a sub-game perfect Nash equilibrium, they have to be playing K in this case. Okay, that's all we're saying. Whereas in the equilibrium in which they can make a commitment, okay, they could be playing U in this case. So here, they've committed to play U, and because they've committed to play U in both cases, suddenly playing L starts to look better for player 1 than playing R. Okay, so if player 2 can make this crazy commitment somehow, then that can influence what decision player 1 would like to make. Okay, so the point of subgame perfect Nash equilibrium is that you rule out these crazy commitments. So you know, it all made sense to you when we went from the back forward, and that's all you do to solve subgame perfect Nash equilibrium. Okay, you look at each of the terminal nodes. You say, look, here does player 2 want to play K or U? They want to play U clearly. Here does player 2 want to play K or U? They want to play K clearly. Okay, so then player 1 has a choice between getting to this terminal node or getting to this terminal node. Okay, so player 1 would like to play R and get to this terminal node. Okay, so we're going to be looking at subgame perfect Nash equilibrium of these multi-stage games, okay, not the Nash equilibrium. So this is all this slide is saying. So in a subgame perfect Nash equilibria, any point in time, doesn't matter what's happened up to that point, doesn't matter if getting to that point is somehow impossible. From that point forward, in the strategies that people are playing, they must be playing a Nash equilibrium. Okay, so at any point in the game, people must be playing a Nash equilibrium.
In these kind of games, at every point is everyone going to payoffs at the end?
Yeah. It's all full information. People look at games with partial information, but they're a lot more tricky. Okay. Maybe in your advanced micro, you might look at some of that. And then this is just a more formal statement of the same thing. Okay. So it doesn't matter too much. The important thing to remember is when you're solving the subgame perfect Nash equilibria, you start at the end. Okay, you solve the Nash equilibrium of all the terminal nodes, and then you work backwards. Okay, so here's a famous game. Have you seen this game before? The Centipede game. Okay, the description of the game I've stolen from Wikipedia. It's a bit lengthy. So you've got two players, Alice and Bob. Okay, and at the start of the game, there's a pile of coins. Okay, in front of Alice. There are two piles of coins. In fact, so one has 4 coins, and one has 1 coin. And she's got a choice. She can either take the larger pile, okay, in which case the other player gets the smaller pile, gets the 1. So at the moment, at the start of the game, Alice has 4 coins and 1 coin, so she can either take 4 coins and give 1 coin to the other player, or she can push both piles of coins across the table. And as she pushes them across the table, magically they double in size. Okay, so the pile of coins that was 4 becomes 8, the pile of coins that was 1 becomes 2. Okay. When she pushes them across the table, the other player then also has 2 piles of coins in front of them. They have the same choice to make. They can either take the money, or they can again push it across the table. Okay, so each time it pushes across the table, the size of these piles of coins gets bigger and bigger. But there's a fixed number of rounds. Okay, so you know, the game ends when someone takes the coins, but the game is also guaranteed to end after a fixed number of rounds. Okay, so well, maybe the coins can go across the table 5 times. Okay, they double each time they go across. So if we started off saying 4 coins, is this going to work? So 4 doubled 5 times, well, 8 is 1, 16, 32, 64, 128. I don't have 128 coins there, do I? So I've got £10 and 20p here. You can guess where this is going. So I must have 50 coins. So we need 4, 8, 16, 32. Okay. So we're going to play this game, and it's going to stop when one of the piles of coins has 32 coins on it. Okay. So the most you can win from playing this game is 32 times 20p, so that's £6.40. So, the least you can win, so if you just play this game, you know, I put the 2 piles of coins in front of someone and they take the coins at the very first round, okay, then the other person is going to get 20p, is going to get 1 coin. Okay, so you're going to get, from playing this game, you're going to get some amount of money between £6.40 and 20p. So it's quite a good deal for you. So, because I imagine all of you would like to play this game, we're going to auction the right to play the game. Whoever bids most gets to play the game. So, who will pay 25p? Yeah, good. We need someone else. 2 people. Okay. Will no one else play 25p? Really? Yeah, 25p. Okay, 30p. We'll play 30. 30. Okay, so we've still got 3 at 30. 40p. We'll play 40p. So we've got 1 at 40. Do we have 2 at 40? Yeah, we've got 2 at 40. Do we have 3 at 40, or do we stop there?
I'll go 50.
You'll go to 50. We've got a big 30. Okay, 50p. Do we have, how many do we have at 50p? 60. Oh, it's getting bigger. Okay, well let's go to let's go to a pound. Who's prepared to pay a pound? 1, 2, 3. Still not. A pound, 40. I'm waiting for one of you to drop out. Well, yeah, they're going to get some money back. It's fine. Yeah, exactly. Pound 40. Pound 20. Pound 20. Have 1 at pound 20. You in at pound 20? Or you, one of you? No? 2 right? Okay. So people seem to have put that at a pound. So maybe you 2 at a pound. Yeah.
Pound 20? Yeah, pound 10.
You'll go to a pound 20?
No, pound, just a pound.
Pound? Well, we'll do a pound 10. I don't want to 17. Okay, so we've got 2 at a pound 10. Okay. Do you want to flip a coin to decide who goes first? So heads is the person behind you. Okay. Heads, okay. So here we go. So you're giving me a pound 10. Yeah. So 1, 2, 3. Okay, so there are your 2 piles. So you're going to take, or you're going to... You don't like to keep your check. You don't like to keep you going to take, or are you going to?
If I give a shit, he's going to take it.
No trust.
Just agree to keep passing it half the at the end.
That's communication. Don't get my there.
Yeah, so I'll consider it.
Okay. Okay, so now it magically doubles in size. So that's now 20p, and this is now 80p. 3, 4.
If anyone took a pile, then we'll have to.
Then it stops. So that's 80p, that's 40.
He can. This is the point.
Sorry, that's 8 toys, isn't it? The hand 60.
Right now, well, if they keep it, but now it's double. He's for free.
So you know, that's now come to be more than you put out.
So what happens in this case?
Did he agree to push?
It's all about your impatience.
Did you push it? You pushed it. I think it's more fun when you know who's going to be the snitch and take the money. I don't think they're taking it once they go Look at Shiv, his eyes are glowing. Okay, this. You guys are playing 2-9.
You know, this is now £6.40. So it's not going to double again.
Yeah, but you can just split it. Just split
He
that.
wants all the money.
No.
Yeah, but if you push it,
No,
then
there's no more pushing.
There's no
You
more.
have to take it. There's no more pushing.
There's no more.
pushing.
And how much is another bar?
What will you? So you get that one, right?
Okay,
You were, okay, so that's yours. You get £6.40. You get 20, 40, 60, 80. So you made a profit as well. You get £1.60. Okay. And you owe 90p change. 20, 40, 60, 80. Okay. Oh, a bit of a side Okay, so when we came down all of that, I've lost a lot of money. I started with £10, right? I now have 20, 40, 60, 80. So I've got a pound there to another £3, £4, £4.20. So I've lost £5 later. Okay, so the first thing we learned is that you guys didn't bid enough, because even the loser there made a profit, even without the side payment. The loser would have made a profit, so you could have bid a bit more. What happened in that game was that they kind of played a commitment strategy. They agreed to do something crazy off the equilibrium path. Okay, so they promised to split the money at the end, which is strictly irrational for him. It's like playing you in the last game. He kind of promised to do something crazy off the equilibrium path, maybe something that wasn't in his best interest, giving the other person the money, and likewise, the other person pushed the money across even in the last period, where really there was nothing to be gained from pushing the money across at that point. But if you've been playing the subgame perfect Nash equilibria, what do you think would have happened?
She would have taken the money.
Yeah, so you just take the money in the very first period. Okay, but the way to see that is that, suppose it's Alice's turn maybe, and the fixed number of pushes has expired, okay, then Alice has no choice but to take the money. So given that's what Alice is going to do in the last period, in the period before, Bob knows that if he pushes the money across, he's going to end up worse off than he would be if he just took it. So Bob should take it in the period before. But then if Alice knows that in the period before that, Alice ought to take the money in the period before that. Okay, and the whole game unwinds back to the very first period. So really, you ought to just take the money in the very first period. So in the subgame perfect Nash equilibrium, everyone takes the money in the first period. What those guys played is kind of like a Nash equilibrium in which they made crazy commitments. Okay, so we don't like those Nash equilibria with crazy commitments, and we're going to stick to nice subgame perfect Nash equilibrium. Okay, so hopefully you learned something from taking my money. So we've done that. So this was just to remind you of some game theory. Okay, so now let's get back to what we're supposed to be doing, namely some oligopoly. So we're going to start with so the general structure is going to be the following. We're going to be two periods. The first period, firms are going to decide whether or not to enter the industry. And if they decide to enter, they have to pay a fixed cost of F. Okay, so even if they don't sell anything, they have to pay this fixed cost of F just to enter the industry. And then those firms that have entered the industry then compete in either Cournot or Bertrand competition. And so they're going to set quantities or prices, and they're going to make some profits. So the way we're going to solve these firms is just like the way we solved everything else we looked at. You start at the last period and you work backwards. Okay, so we'll start with symmetric Bertrand competition, which would be nice and easy. Okay, so Bertrand competition, firms setting prices, remember. And we're going to assume that all potential entrants have the same marginal cost, which will make our life easier. And we assume that the monopoly profits I M star, so that's the profits a firm would get if there was only one firm in the industry. We assume that those profits are bigger than the fixed cost. Okay, so if only one firm entered the industry, at least that firm would make some profits. So to solve this game, like I said, we start at the end and we work backwards. Okay, so how many terminal nodes are there here? There could be quite a lot. There could be one firm entering, there could be two firms entering, there could be three firms, etc., etc. So let's go through them in order. We'll start with one firm entering. So if one firm enters, decides to pay the fixed cost, then in the second stage, it's just going to choose the monopoly price, okay, and it's going to make monopoly profits. So if just one firm enters, it's going to make a profit of pi n star minus F. This is monopoly profits. Okay, so if one firm enters, it's happy, it makes a profit. If two firms enter, then what's going to happen in that second stage of price competition? Go on.
All firms have to set price equal to marginal cost.
Yeah, exactly. So, Bertrand competition, price gets driven down until both firms are setting the same price, namely their marginal cost. Okay, so in the second stage, those firms aren't going to be making any profits at all. So if two firms entered, they've made no profits from the second stage, so their overall profits would be negative. They make a loss overall. They pay this fixed cost, but then they don't make any profits from production. So if for three firms entering, it's going to be just exactly the same. Okay, they're all going to make a loss of the fixed cost and make no profits in the production stage. So how many firms are going to enter with entry then Bertrand competition? Yeah, exactly, just one. So, what we get with Bertrand competition, when there's this entry decision, is that only one firm enters, and you get the monopoly price level, the monopoly distortions. Okay, so you think of Bertrand competition as this magical, efficient thing that gets price equal to marginal cost. In fact, when there is some entry costs, what's going to happen is Bertrand competition just gives you the monopoly outcome. because only one firm wants to enter the industry in the first place. So, you know, what you thought about what type of competition was efficient might be a bit wrong. And the idea is that we get monopoly precisely because if there was competition, it would yield an efficient outcome. You know, because the competition is so fierce, if there are multiple firms in there, in fact, only one firm will enter. Because if two firms enter, then both lose. And there's a question here, when potential entrants have different marginal costs, which of them would enter? Yeah, exactly. So, you know, that's good that we get the firm with the lowest marginal cost producing, but they're going to be selling a high price, there's going to be a dead weight loss efficiency loss in there. So Bertrand competition is quite easy to solve in this multi-stage version. And I ask here, when's welfare improved by the government paying the entry cost for two firms? So, you know, maybe if you've got a situation like this, it might be a good idea for the government to step in and say, look, I would like some competition in this industry, I'm going to pay one of your entry costs. Okay. So, sorry, two entry costs. Okay, if two firms are in the industry, they're both going to make zero profits. Okay, so for them to be prepared to enter the industry in the first place, the government is going to have to cover all of their entry costs. Okay, so is it a good idea for the government to come along and say, look, I'll pay the entry cost of any firm that enters this industry? So maybe nuclear power or something. It's very hard. The costs of setting up a nuclear power plant are incredibly high, but you'd like some competition in the energy produced by nuclear power plants. So maybe it's a good idea for the government to pay for the nuclear power plant to be built in the first place. And this is going to be welfare improving just when the deadweight loss due to monopoly is bigger than the fixed cost. So how to explain this? Well, so welfare is consumer surplus plus producer surplus, and here we're going to have an extra term, which is minus this amount that the government's paying. So if the deadweight loss due to monopoly is bigger than the fixed cost, okay, then if the government pays for one firm to enter, okay, so the way to think about this is, if one firm is entering, okay, then one firm is paying the fixed cost already. That fixed cost is just like deadweight loss, it just disappears. You know, it's not productive, the fixed cost. Okay, so each firm that pays the fixed cost, that's a net loss from total welfare. Okay, the fixed cost just disappears into the ether. So we want to go from a world in which one firm pays the fixed cost to a world in which two firms pay the fixed cost. So for that to be an improvement in welfare, the gain, okay, the gain from paying two, which is you gain this deadweight loss from monopoly back, has to be bigger than the cost, which is paying for the second fixed cost. Okay, so you know, in terms, you can write down welfare. So welfare is going to be consumer surplus plus producer surplus minus n times the fixed cost. Okay, it doesn't matter who's paying the fixed cost for welfare. You know, when one firm is entering, that firm is paying the fixed cost. But you know, in terms of welfare, it doesn't make any difference if one firm is paying the fixed cost, or if a firm is paying the fixed cost, or if the government is paying the fixed cost. Okay, so this is, you know, think of this as producer surplus from the production period, and this is consumer surplus from the production period. When one firm is paying the fixed cost, okay, it's like kind of net producer surplus is production period profits minus the fixed cost. Okay, so for one firm paying the fixed cost is like the fixed cost that's coming from producer surplus. When the government is paying both fixed costs, well, you know, the government has to tax some consumers in order to pay for that. So it's likely fixed costs are coming from total consumer surplus. But in terms of welfare, you don't care if it comes from consumer surplus or producer surplus. So all you need is that the gain, which is this deadweight loss of monopoly, is bigger than the cost, which is you know, we can simplify this a bit. Well, what's deadweight loss? Well, you know, here's a demand curve. Here's a marginal cost curve. Maybe the monopolist is selling a quantity Q star. Okay. And so the price is going to be up here on the demand curve. And the deadweight loss, which is this area here. No, sorry. The deadweight loss. If you had perfect competition, the price would be here, right? Where price equals marginal cost. Okay. So this is marginal cost. This is PQ, demand curve. If you had perfect competition, the price would be there. So the deadweight loss is this area. Does that make sense? So, you know, you can write that in an integral. Here's the quantity produced under monopoly. Here's the quantity produced under perfect competition, which I'm calling Q star PC. So the deadweight loss is an integral from Q star M to Q star PC of the price minus marginal cost. Okay. In the simple case where marginal cost is this constant. So this condition is going to be true if this integral is bigger than f. And I set as an exercise to simplify that condition in the special case with linear demand. You know, just to see if you're comfortable working with these integrals. Okay, so that's all we're going to say about Bertrand. People are falling asleep already, apparently. And now we're going to go on to symmetric Cournot. Okay? So we're going to assume isoelastic demand. So the price set is going to be K times Q to minus beta, the price people are prepared to pay. And this is a inverse demand curve. And all firms are going to have constant marginal cost C again, for simplicity. And what we showed in the exercise from last week, you know, if you want to see the derivation, look at the YouTube video of the class online, was what the price under Cournot competition was given by this expression. It's the marginal cost divided by something. Here n appears here. As n goes to infinity, this bit is getting smaller and smaller, and price is going to marginal cost. Generally, for n less than infinity, price will be bigger than marginal cost. Price will be some markup over marginal cost. And if you just substitute this price into the demand curve, you can find out what the market quantity is. Okay, and the market quantity is just given by that. So what do we say? P is C times 1 minus beta over N. And we know that P is K times Q to the minus beta. So we want to solve this expression for Q. Okay, so let's divide by K to start with. So C over K minus beta K over F. Okay, we just divide both sides by K. And then we've got a negative power here, so let's just invert both sides first. Okay, so this is K minus beta K over N, all divided by C is Q to the beta. Okay, we just done 1 divided by both sides. And then all we have to do is raise to the power of 1 over beta. And then we get Q is K minus beta K over N over C, all to the power of 1 over beta. And what have I got on the board? So if you times top and bottom of this fraction by N, okay, you get NK minus beta K over NC. That's what's written in the board. So this is the same. So this was for price, this is for quantity. So what are firm's profits going to be? Well, constant marginal cost. Do you want me to write it on that board as well? You sure? It's price. It's going to be price minus marginal cost. Okay, that's the revenue they make on each unit, the profits they make on each unit, times the total quantity they sell. Okay, which is for n firms in the industry, so the quantity sold by each firm is total quantity divided by n. Okay, so this is price minus cost all times constant. So that's the profits they're going to be making for a production period. We can substitute in this messy expression for quantity, and you can write profits as this thing. Okay, I've substituted in the price first, so the price has gone in there. And then I substitute in this expression for quantity. Okay, so there's the expression for quantity. Here's the expression for price. I've just rewritten it a bit. So the n here has come there, and I times top and bottom by n. Do it on here. So we have this thing, let's just look at this thing in brackets. Okay, just check my maths is right. So we've got C, 1 minus beta over n minus C. Okay, well that's equal to C times n over n minus beta, or minus C. Okay, let's combine the two fractions. So let's treat C. So C, we know C is equal to C times n minus C times beta, all divided by n minus beta. See that? So we can combine the two now as C times n minus C times n minus C times beta, all over n minus beta. C times n beta cancel, minus minus makes a plus. Okay, so this is C times beta over n minus beta, which is what I've got there. Okay, so this thing in brackets is this thing in brackets. The divided by n has come there, and Q star is just straight from there. So this is a messy expression. Don't worry too much about it. We're just gonna use it to answer a question, an empirical question that has bothered a lot of empirical industrial organisation people. So it turns out that in the real world, firms seem to be larger in large industries, and it's not obvious why that should be the case. You know, you might think if there's a lot of demand, you get so much entry that actually firms get smaller in large industries. Okay, and what we're going to show is that you can generate the same regularity under Cournot competition from this. So this is messy, but don't worry too much about it. Okay. So how many firms are going to enter? Well, you know this is the profits they're going to make in the production period. Okay, so if they enter, they make those profits. These profits are a decreasing function of the number of firms. The more firms there are, the less profit each individual firm is going to make. So if the production profits were bigger, if production profits were smaller than the entry cost, okay, then how would firms want to change their behaviour? So you know, it's like firms pay £100 to enter the industry and they make £80 in profits once they've entered. They're just not going to want to enter that industry in the first place. Okay, so we know that the profits they make from production have to be bigger than the cost they pay to enter the industry. but they also can't be so much bigger than another firm would like to enter. Okay? If the profits were so high that if another firm entered, that new entering firm would also make higher profits than the entry cost, then that firm would like to enter in the first place. Okay? So in an equilibrium, the number of firms entering must be the biggest integer such that the profits are bigger than the entry cost. Okay, so as many firms enter as possible such that all firms are still making profits overall. Okay, if one less firm entered, then one of the firms that didn't enter would like to enter. If one extra firm entered, everyone would make negative overall profits. Okay. So it's like firms carry on entering until the profits from production are roughly equal to the cost of entering. Okay, and if the number of firms is large, you can just say that this thing will be approximately equal to this thing. But profits from production under free entry will be roughly equal to the entry cost. Firms are going to carry on entering until the amount they make from production is equal to the amount that they pay. Okay, the only complication is that you can't have 2.5 firms entering an industry. So, but for all practical purposes, under free entry, what we're going to get is that the cost of entry, F, are going to be roughly equal to the profits. Yeah, this is what we've got written here. This is the production period profits. This is the cost of entry. So what I was talking about before was the effect of the size of the market on the number of firms in an industry, okay, and the size of those firms. So how do we measure the size of the market here? Well, we said that our demand curve was P is K times Q to the minus beta, right? I think that's what I said. P is K times Q to the minus beta. So, it's hard to, from looking at this, it's hard to see what the size of a market is, because this is giving price as a function of quantity. To see how big the size of a market is, it'd be clearer if we could see quantity as a function of price. Okay, so let's just rearrange this to get quantity as a function of price. So, let's start by taking everything to the power of 1 over beta. So we get P to the 1 over beta is K to the 1 over beta times Q to the minus 1. Okay, we've got Q to the minus 1 here, let's take it over to the other side. So we get Q, and let's take this over to that side. It is K to the 1 over beta times P to the minus 1. So K to the 1 over beta is kind of the thing that's scaling demand. So that's a measure of the size of the market here. If you hold price fixed and you double K to 1 over beta, then that's doubling demand. In fact, for any price, if you double K to 1 over beta, that's doubling demand at any price. So you can think of this as kind of a measure of the overall level of demand for the product. So beta is giving you the elasticity of demand for the product. K to 1 over beta is giving you how much demand there is overall. Okay, so what we want to know is the relationship between the number of firms in the industry and the size of the market thing, K to 1 over beta. So here was our free entry condition. Okay, and if you look at this, we've got a K inside these brackets, right? But we've got K there and K there. We can take it out of the brackets. Okay. So you can take K outside of the bracket, you get a K to 1 over beta. Let me write something down so you can see. You can think of. Oops. Sorry. Confused. So let's just look at this thing here. Okay, so what is that? Well, it's k times n minus beta over Cn. That's an n minus beta over Cn. Okay, all to a power of 1 over beta. Okay, so that's equal to k to the power of 1 over beta times n minus beta over Cn, all to 1 over beta. So we can take a k to the 1 over beta out, okay, and then we can take everything else over to the other side, just divide through by everything else. And that's what we get on this equation. Well, we flipped everything, we've done it the other way. So this is just an immediate rearrangement of that last equation. Okay, what we have on the left here is n divided by k to the 1 over beta. So this is the number of firms divided by the size of the market. So if the number of firms grew linearly with the size of the market, this thing shouldn't be a function of n. Okay? You know, if you double the size of the market, and that doubled the size of the number of firms, then this ratio would be roughly a constant, right? Okay, this is the ratio between the size of the market and the number of firms. Okay, so this is telling you how the number of firms changes as the size of the market increases. And what we have to see on the right-hand side, we've got an n here, we've got an n there, we've got an n there. What's going to happen to this right-hand side as n goes to infinity? It's going to get smaller, exactly. So you've got an n over n here. So this isn't going to do much as n goes to infinity. This is just going to go to a constant. But this one here, well, that's going to dominate. Okay, so as n goes to infinity, this whole thing is going to get smaller and smaller. Okay, so this thing is getting smaller as n goes to infinity. So as the size of the market increases, the total number of firms is not increasing linearly with the size of the market, it's increasing less than linearly. You know, so if you double the size of the market, this is saying, you less than double the number of firms. Okay, and if you're less than doubling the number of firms, those firms that are there must be getting bigger. So this equation is telling you that firms are going to be larger in large industries with high overall size. And the intuition is the following. You know, if the price didn't change as more firms entered, then as the size of the market increased, the number of firms would increase proportionally to that. But in fact, the price does change as the size of the market increases. As the size of the market increases, more firms enter. As more firms enter, there's more competition in the industry. Price gets pushed closer to marginal cost. Okay? And because price is closer to marginal cost, it's now less profitable to be in that industry, so fewer firms want to enter. Okay, so this fact that price is getting lower and lower reduces some of the incentives to enter the industry as the size of the market increases. Yeah, so this is why you're going to get firms being larger in larger industries. And there's a lot of empirical evidence for this. So Campbell and Hockenheim in 2005, they regress average firm size on the number of firms and various controls, and they find precisely that firms are larger in large industries, and consistent with this Cournot story. And then Shannon and Rice, they also try and test the same thing. So what they do is they call the market size that's required to support exactly n firms, Sn. Okay? So if market size and the number of firms were growing proportionally, then Sn plus 1 over Sn, so the number of firms required to support n plus 1 firms, divided by, the size of the market required to support n plus 1 firms, divided by the size of the market required to support n firms, that would then be roughly equal to the growth in the number of firms, n plus 1 over n. But if this Cournot story is true, then to support n plus 1 firms, you'll need an extra size of a market. Okay? You'll need a proportionally bigger market than the growth in the number of firms. So if the Cournot story is true, this ratio must be bigger than this ratio. Okay? So you need a bigger market to support n plus 1 firms than is just suggested by looking at the ratio of n plus 1 over n. Yeah, so this is clear, isn't it? To grow by 1 firm, market size needs to grow by a larger amount than the number of firms. That's all they're testing. Okay, and what they find is this holds well when the number of firms in an industry is less than about 4. Okay, so if you've got 1, 2, 3 or 4 firms, then this is reasonable. But beyond 4 firms, these two things seem to be about equal. Okay, so beyond 4 firms, it seems that the extra firms entering are no longer having any effect on the price. Okay, beyond 4 firms, in reality, it seems like if the size of the market grows, the number of firms grows proportionally. So this is suggesting that beyond 4 firms, we're getting closer to perfect competition than is suggested by the Cournot model. Okay, so the Cournot model might not be perfect when there are lots of firms in an industry. Yeah, and I'm going to stop for a break there because you're all looking dead.
No, I want to
someone might have to calculate, just figure it out.
Micro is just who's teaching micro now? Maybe it's time to learn some more. The guys who got it last year got such bad attitudes. Who's teaching it?
Remember this ratio?
Oh, something.
Always, and it's usually. It's just never something. It's always just a little bit more than others. Especially now they're hiking. Oh, I see that with
Okay, right, let's get going. I know this is a bit painful, but it's once you're slightly familiar with this stuff, it won't seem quite as painful as it seems now, okay? But if you go over the exercises from last week, and a lot of this stuff will start to make sense. So the other thing we want to look at is welfare control. Welfare under Bertrand was really easy. Okay, we got one firm entering. It's just the same as welfare under monopoly. Welfare under Cournot is going to be a little bit more tricky. Okay, so remember the total social surplus is consumer surplus plus producer surplus. So, draw the diagram I had before. Here's price and quantity. Demand curve. Here are some costs. Here's the quantity that's being produced. Price is this one. Okay, so the total social surplus is producer surplus, which is this bit, plus consumer surplus, which is this bit. Okay, so total social surplus is the integral of the difference between the demand curve and the marginal cost curve for quantities from naught up to the quantity that's being produced. Okay, so total surplus is all of this. And when we look at welfare, we always care about total surplus, not one or the other. Okay, with constant marginal costs, it's a bit easier. Okay, so it's the integral from naught up to quantity being produced and price minus cost. And we also have to correct for the number of firms that are entering because they're all paying these fixed costs. Okay, and remember each firm that pays for fixed cost, that's just wasted, paying for fixed cost. Okay, the money just disappears into the ether, it's not producing anything. So welfare is, the standard expression for welfare minus this extra term which covers the loss due to paying this fixed cost. Okay, and Qn star is the quantity that's produced within firms in the industry. So what we want to know is, well, let's suppose that we leave the industry alone. Okay, firms decide whether or not to enter the industry. So until the profits from entering reaches the costs of entering. We want to know if the government should step into that industry and encourage more firms to enter or discourage firms from entering. Intuitively, would you think too many firms or too few firms would enter with other competition? Too few. Okay, well, so why do you think too few?
If there's a fixed cost to entering, we've already seen that.
Yeah, okay, so with Bertrand competition, too few firms entered. You would have liked 2 firms to enter, but in fact only 1 firm entered. And yeah, it's plausible the same thing would hold here, so we'll see if it does. Okay, so what we want to do is we want to see how welfare changes as you add extra firms. Okay, so we want to differentiate welfare with respect to the number of firms. So here's our expression for welfare. Now, we've got n is in the upper limit of the integral. Okay, that's going to make our life a little bit tricky. And n is here as well. But remember, remember, maybe you've got something called f of x, okay? This is just a reminder for you. Let's just suppose you have this thing called f of x, which was defined as the integral from 0 up to zx of f of z dz. Then what would the derivative of f of x be? fz, exactly. So remember that integration and differentiation are kind of the opposite of each other. Okay, so if you've got an integral that's going up to the argument of the function and you differentiate that, all you get back is the inside of the function at the end point. Okay, so f dashed of x, the derivative of f of x is just going to be f of little x. You must have seen similar things to this in statistics, right? This looks like a cumulative distribution function, and that looks like a probability density function. Okay, and if you differentiate a cumulative distribution function, you get the probability density function back. Is this completely alien? Okay, so this is just something useful to remember. When you're differentiating an integral, you get the thing inside the integral evaluated at the end point. So now what we know. So let's do this in two parts. Okay, so we've got. Let's first do the derivative of this integral. Okay, from 0 up to q. Let's say q star of. Is it pq minus c pq? Let's do the derivative of that with respect to q star. Okay, and that's easy, right? We've seen how to deal with derivatives like this. It's just the thing inside evaluated at the end point. Okay, so it's just derivative of this expression with respect to that thing there, q star, is just the thing inside, pq star minus c. But what we have here is we're not differentiating with respect to q, we're differentiating with respect to n. Okay, so we have to combine this rule with the chain rule. Remember that you remember the chain rule? So if you've got the derivative of f of g of x with respect to x, okay, that's the derivative of f of x that thing is f dashed of g of x times g dash of x. The chain rule. You've seen this before. Okay, so we're gonna apply the chain rule to this derivative. Okay, the thing with the chain rule is the derivative of the outside evaluated at the inside times the derivative of the inside. So here we want the derivative of all of this with respect to n. So we're first going to do the derivative with respect to q, and then we're going to times it by the derivative of q with respect to n. So the derivative of this integral from 0 up to q n star, okay, p q minus c dq with respect to n. Okay, that's going to be the derivative with respect to q, which we've already worked out as this thing, p q n times the derivative of qn with respect to n. Yeah, I'll write it on this side and then discuss it. Do you want to point the camera around? Yeah, I'll go from the start again. So what we're doing is for derivative with respect to n of this integral from 0 up to q n star of p of q minus c dq. Okay, and we're doing that in two stages. First we do the derivative with respect to q outside, and then we're multiplying by the derivative of this thing, the inside, qn star, with respect to n. So that's just the chain rule. Okay, so rather than directly tackling the derivative with respect to n, we're first differentiating with respect to qn, and then we're differentiating qn with respect to n. It's just the normal chain rule. Okay, and what we said is that the derivative of an integral with respect to this upper limit is just the thing inside, okay, evaluated at the upper limit. So all of this thing in brackets is just p q star n minus c. And then we just have this term left, d q star. Okay, it's a bit annoying, I know, but it's just two tricks in a row. That's why it seems so confusing. Okay, are people broadly happy? You know, it's unlikely you're going to have to do too much of this manipulation of integrals in an exam, but you know, still, if you want to be able to discuss the welfare properties of these models, it's still useful to see where these things come from. Okay, I don't want to say it's a complete waste of your time to look at this stuff. You know, I want to convince you that what I say is true, right? So it wouldn't be very satisfying if I just said, this is a theorem, but you could prove that you could be bothered. You know, I want to show you why things are true, rather than just telling you things are true. You know, it's not too hard, I think. You can handle it. So the derivative, thank you. The derivative of welfare with respect to the number of firms is this expression here. Okay, that's what we've got to. So we want to know if adding another firm increases welfare or decreases welfare. So we want to know if this is positive or negative. The first thing we're going to do is we're going to evaluate this at the number of firms to enter under free entry. Okay, if you leave a market to itself, this number of firms, n star, we're going to enter, where n star was the solution to the messy equation we had before. You know, n star was the solution to this. And we remember, you know, the free entry condition, what it said was that in equilibrium, the cost of entry must be approximately equal to the profits you make from entering. Okay, the profits you make from entering are the price evaluated at the equilibrium quantity minus cost. That's profits per unit times the total number of units each firm sells. Okay, so the optimum number of firms, for the entry cost equals production period profits. That's all that's saying. So what we're interested in is the derivative of welfare was this expression here. Right, that's what we had on the last slide. This expression. And this expression looks quite similar to this expression. So we're going to use that to simplify that. So how do we change this expression into that expression? Well, we've got this extra bit there, okay, and we've lost a bit. So we've gained a bit and we've lost a bit. So this thing here, remember that all of this is equal to f, okay? So if we do f, where's f? If we do f times n over q star, so f times n over q, well, we've multiplied the right hand side here by n over q, so we multiply the left hand side by n over q, okay, and all we're left with is this bit, okay, we put in brackets. So f times n over q is equal to p of q minus c. What we were trying to get to was this expression, so we have a derivative on the end. So again, if we multiply both sides by the derivative, what is it, dqn star dn. Okay, so now we've expressed this thing, which was a bit messy, as this. dqn star dn times f times n over qn star. And that's all I've written on the board here. Okay. So because of a free entry condition, you know that this expression is equal to this expression. Okay, this is a tricky proof. You know, you're not going to have to replicate this in the exam, don't worry. But you can still pay attention. Okay, so what are we doing? Yeah, I do know what I'm doing. So we've got this thing must be equal to this thing. Okay, this, maybe we can do something with this. Okay, so the next strange trick we're going to do is we're going to take n squared over q out of the brackets. Okay, so if we take n squared over q out of the brackets, we've got n over q here, so that gets rid of most of that. But we need a divided by n here. You know, 1 divided by n times n squared gives us n. Okay, which gives us that n. And we're divided by q here, it becomes divided by q there. And then if we've got n squared over qn here, we need qn over n squared here, so that times that makes 1. Okay? So we've just taken n squared qn star out of a bracket for some mysterious reason. And the reason we do it is because this thing here is just the derivative of a ratio. So look at this thing in brackets, right? And what I'm claiming is that this thing in brackets is the derivative with respect to n of qn over n. So you know the rule for differentiating a ratio? So derivative with respect to n, so u over v, is u dash v minus v dash u over v squared. Don't you remember that from your A-level maths formula book a long time ago? Yeah, so derivative of this ratio, well, it's derivative of the top, so there's the derivative of the top, times the bottom divided by the bottom squared, so that's just divided by the bottom, minus the derivative of the bottom, well, derivative of n with respect to n is just 1, okay, divided by u over v squared, the top over the bottom squared. Okay, so this thing, in brackets, is just this thing. Okay, so what we've proven is that the change in welfare as you add an extra firm is something that's positive times the change as you add a number of firms of the quantity produced by a particular firm. Remember, qn star is total quantity, so qn over n is the quantity produced by one firm. Okay, as you add more firms, the quantity produced by each firm has to go down. Okay? You know, you can show that if you wanted, but it's just obvious. So this thing has to be negative. So the conclusion of all of this horrible maths is that if you look at welfare, as you increase the number of firms, welfare decreases. So are there too many firms entering or too few? Too many? Yeah. So under Cournot competition, it's not that too few firms enter, it's that too many firms. Too many firms enter. Welfare would be improved if you paid some of those firms not to enter the industry. And the intuition is that when another firm enters the industry, they're going to push down the price for everyone. Okay, so another firm entering the industry is going to hurt the profits of everyone who's already in the industry. So, you know, me as the owner of another firm who's considering entering, you know, I've got too strong an incentive to enter because I don't realise the harm I'm going to do to everyone else by entering. You know, when I enter, I only care about my own profits. But in fact, by entering, I'm harming the profits of everyone else. So it's like there's a kind of negative externality to my entry decision. Okay, and this
Surely
is
if you're harming profits of financial consumers.
yeah, that's yeah. So you know, there's always a trade-off between consumer surplus and producer surplus. Yeah, it's not obvious. It's not. That's it's a good point, isn't it? So consumers. Well, look. Remember that there's this fixed cost as well. So when another firm enters, you know, there's quite a big cost to everyone from covering this fixed cost, if you like. Yeah, but I take why it's not completely obvious. You're right. Well, no. Sorry. Let me start again. It was a very good question. What matters for welfare, okay, is so the optimal number of firms would be entering if the incentives of a firm to enter were in line with the incentives of society, okay. And what we're saying is that because a firm does this. Does damage to the profits of everyone else, okay, that means their incentives are too strong. Now what you're saying is that they're doing damage to someone else's profits, but they're increasing consumer surplus. But that's, and you're right, what's happening is there's some kind of transfer between consumer surplus and producer surplus going on, so the price goes down. But still it's the case that the individual, the new firm entering, he has too strong incentives to enter. You know, because as far as society is concerned, you would like the firm to internalise all of the effects of their entry. I'm not sure I've completely convinced you, or I'm not sure if I've completely convinced myself, to be honest. But so you know, you've got two ways of showing this to yourself. One is to do the maths. The other is to believe my woolly intuition. Neither is completely convincing, I guess. Maybe see if Oz Shy gives a better intuition. This is the important effect. I'll have a think and see if I can give you a more convincing story later. Okay, so in the last 20 minutes, I just want to talk a little bit about Cournot versus Bertrand. I'm not sure how far we'll get. Okay, so on the Bertrand competition, firms are setting prices, and the Cournot competition, firms are setting quantities. With Bertrand competition, the quantity is adjusting to clear the market. Okay, we understand how quantities can adjust to clear the market. You know, firms just carry on selling until no one demands anything anymore. So it's nice and easy to see how quantities can clear the market. And the Cournot competition, firms are setting quantities and then prices are adjusting to clear the market. And that's a bit strange, right? It's not clear how these prices should be adjusting in the Cournot competition. You know, so on the Cournot competition, it's as if there's an auctioneer who's selling the good. Firms are choosing the quantities they want to produce, and then an auctioneer magically sells all that quantity, so you end up at a point on the demand. You know, so maybe it makes sense for large manufacturing firms like aeroplanes. There aren't many aeroplanes being produced. Boeing and the other one, Airbus. are deciding the quantities they want to produce, and then it's plausible that there's some kind of auction that's determining the prices once they've chosen the quantities. But for other things, it's a bit harder to see how this might work. Okay, so what we're going to see is a model that will generate something like Cournot, but without this mysterious auctioneer setting prices that makes Cournot strange. So this is, what we're going to look at is a two-stage combination, if you like, of quantity and price setting. And it's due to a very famous paper by these guys, Krebs and Shankman. So in the first period, firms are going to invest in capacity. Okay, they're going to be able to produce any quantity up to their capacity. In the second period, they're going to compete in prices, subject to the constraint that production has to be less than capacity. So you can't produce more than you invested to produce. So if you like the capacity investment, that's building factories. The factory can only produce so many million cars. You can't produce more. You can't sell more cars than your factory can produce. Okay, so like any game, we're going to start in the last period and work backwards. So let's suppose that firms have chosen some capacity. Let's see what prices they want to set in the second period. Okay, so there are two firms, both with zero marginal cost. Firm I has a capacity constraint of QI bar, so their quantity can't be higher than QI bar. And we just suppose they're exogenous for now. And firms are going to choose prices PI, with the market demand Q of P. So let's suppose that firm 1 is setting a price P1, which is less than the price set by the other firm. And at this price they're setting, the quantity demanded is bigger than the quantity they can supply. The Q1 bar is their capacity, this is demand at the price. Okay? So what happens if the demand is higher than the supply? Well, not all of those consumers can be sold for good, right? There's no way for firm 1 to produce more than Q1 bar, so some of those consumers have to be rationed in some way. And there are two types of rationing that the literature considers. One is called proportional rationing, and the other is efficient rationing. And the way you think about proportional rationing is that it's as if consumers, everyone wants one unit of the good, and everything we're looking at now. Okay? They all have different reservation prices. And with proportional rationing, it's as if everyone leaves the house at different times, random times during the day. Okay, so some of you will randomly decide to go shopping very late at night. Some of you will randomly decide to go shopping very early in the morning. If you go shopping very late at night, there's a chance that we've already run out of the stock. Okay, but just because you value the good very highly, it doesn't necessarily mean you're going to go shopping any earlier. Okay. So what's going to happen? Well, the price P1. There's a total of Q P1 consumers who want to buy the good at that price. Okay, but only Q1 bar of them can be satisfied, because that's the capacity constraint for M1. So, if you're arriving randomly at this shop, what's the chance of you being rationed? And then if you get rationed, you have to end up buying from firm 2 rather than from firm 1. Well, the total demand of the price P1 was QP1. How many people are going to end up rationed? Well, Q1 bar people, they're going to actually be able to buy the good from firm 1. So the lucky people who turn up in the morning, they're going to buy the good from firm 1. QP1 minus Q1 bar, they're the people who get unlucky and they get rationed. Okay, these people are the guys who turn up late to the shop and they've sold out to everything. Okay, so if you're someone randomly choosing when to wake up, the probability that you get rationed and you have to buy from a second firm is this ratio. Okay. So if you get rationed, you're then going to consider buying from a second firm. So the second firm is charging some price P2, and let's draw a demand curve. Okay, right. Quantity, the demand curve. P1 was low, P1, P2. Okay, so here's here's QP1, that's kind of the number of people who want to buy at the price P1. What proportion of all of the people who want to buy at the price P1 want to buy at the price P2? Well, it's just QP2 divided by QP1. So if you're a random person who would like to buy at the price P1, then the chance that you'd also like to buy at the price P2 is just this ratio. Okay, so the demand that's going to be left facing the higher price firm is total demand times the probability that total demand that people get rationed, okay, which is this one, times the probability that if you get rationed from the first firm, you'd like to buy from the second firm, which is that guy. Okay, so the residual demand curve that's facing firm 2 is given by this expression. Okay, and you can see this graphically. Yeah. Okay, so here's the original demand curve. Q1 bar consumers, they get to buy at the price P1. They're lucky, they turn up early in the morning. They get to buy at the price P1. Okay, so that number of consumers just disappears from demand. They've been satisfied by the first firm. So the consumers that are left of the second firm, they effectively have a demand curve that just looks like this. So all we've done is kind of rotated the demand curve so it goes through this new point. Okay, and that's what proportional rationing does. Is this kind of rationing efficient? Well, you can probably guess from the other type of rationing being called efficient rationing, that this one isn't going to be efficient. And you're right. You know, so suppose Alice values were good at less than P2, but more than P1. Okay, so Alice would like to buy from a cheaper firm, but not from an expensive firm. If Alice wakes up very early in the morning, you know, she's lucky, she gets a good draw, she's able to buy the good at the cheap price. But maybe Bob values the good at more than P2, more than the high price even. But maybe Bob's really unlucky, okay, and he wakes up very late. Then, by the time Bob wakes up, firm 1 is sold out, and maybe firm 2 is sold out as well. So Bob would like to pay Alice to buy the good. Okay, so the fact that there are people who are gains from trade means that it can't be efficient. Okay, even after all of this buying and selling has taken place, there are still some gains from trade left on the table. So this type of rationing can't be efficient. If we want to get efficient rationing, we have to change the assumptions slightly. So rather than people going to the shops at random times through the day, to get efficient rationing, we have to assume that people who really value the good, they wake up really early in order to get to the front of the queue. So it's like when the new iPhone comes on sale, you always get these queues outside the Apple shop in London. Okay, the real Apple fanboys are prepared to camp out overnight in order to buy the new iPhone. Okay, so if you really like the good, you're prepared to get to the shop really early in order to avoid being rationed. So which consumers are going to get to buy the good? Well, the Q1 bar consumers who have the highest valuations. You know, they're the ones who are prepared to camp out outside the shop. So what's the residual demand facing the second firm going to be? Well, it's just going to be total demand less these consumers who camped out and bought from the first firm. Okay. And you know, it's also easy to see this in the graph. Okay, with proportional rationing, we rotated the demand curve. With this efficient rationing, here's the original demand curve. Q1 bar consumers buy from the cheap firm. Okay, you know, they're the ones who have the highest valuations up here. And what's left is just a parallel shift. Okay, so there are two ways, the point of all this is that there are two ways we could conceivably model rationing. And in fact, you can think of a continuum between these two extremes of proportional rationing and efficient rationing. Efficient rationing is going to be efficient, and this is kind of skin down. And what type of rationing you use is going to make a difference to how this Bertrand composition is going to work. Okay, remember, we're imagining the case in which firm 1 was setting a price such that the demand of that price was above their supply. Okay, so let's just assume efficient rationing for now, then, and we're going to assume linear demand as well, 1 minus P, as easy as it can be. And our claim is that both firms charging a price equal to 1 minus the total capacity is going to be in equilibrium. Okay, so remember, this is the maximum quantity that these two firms can supply. At least as long as these quantities are both less than a third. Okay, it's a technical condition. If we want to see if this is an equilibrium, we have to check two things. Okay, first we have to check the firms don't want to increase their price, and then we have to check the firms don't want to decrease their price. So if they decrease their price, well, they're already selling at capacity. Okay, they're already, the total quantity being sold is the total quantity that's being produced. Okay, so if they decrease their price, they're not going to sell any more units because they're already at capacity. So all that's going to happen is they make less profit on every unit they sell. Okay, so if a firm is at capacity, it certainly doesn't want to decrease its price. So no firm wants to undercut the other. So we just have to check that they don't want to increase their price. Okay, that's what we do on the next slide. Well, let's see. Will the firm like to deviate to a higher price? Okay, then if they did, they're faced with a residual demand curve. Okay, remember with efficient surplus, the residual demand curve was the original demand curve less the quantity sold by the first cheap firm. Okay, so the demand curve firm 2 is going to face is going to be 1 minus the price they set minus the quantity sold by the other firm. So what are their profits going to be? We said marginal cost was 0 here. So profits are just price times quantity. And let's look at the derivative of profits at this optimum price. Okay. So here's profits. The derivative of profits with respect to P2 is going to be 1 minus 2 times P2 minus Q1 bar. Okay, let's evaluate that at this the price we said was the optimum, this one. Okay, so we're just substituting that in for P2. Okay, that's all we've done here. And so we've got 1 minus 2, so that becomes minus 1. We've got minus 2. We've got minus 2 times minus Q1 bar, so that's 2 Q1 bar minus Q1 bar. Okay, so plus 2 minus 1, that's 1 Q1 bar. And then we've got minus minus is making a plus, so we've got plus 2 Q2 bar. And we made this technical assumption earlier that Q1 bar is less than a third and Q2 bar is less than a third as well. Okay, so if this is less than a third, this is less than a third, so 2 times it is less than 2/3. So all of this must be less than 1. Okay, so the whole thing must be negative. So what we see is that if profits are at the optimum point, then if they increase their price, profits go down. Okay, the derivative was negative. So firm 2 doesn't want to deviate to a higher price either. Okay, they don't want to go to a lower price, they don't want to go to a higher price. So this is an equilibrium. Okay? So we've solved the second stage game, at least given some assumptions. What we have to do is go back and look at the first stage game. And let's suppose that the cost of investing in a unit of capacity is 3/4. Okay, I've carefully chosen it so that the maths is nice and easy. So the first thing we're going to do is get a bound on the maximum revenue that they could get in the second stage. Okay, so if they chose an infinite capacity in the first stage, okay, then there's lots and lots in capacity, and the second firm chooses 0 capacity, then it's just monopoly, right? Okay, if one firm produces, is prepared to produce an infinite quantity, the other one can't produce anything, then it's just like a monopoly setup. Okay, so the revenue from the second stage must be less than monopoly revenue. There's nothing they can do to beat monopoly revenue. What's their revenue on the monopoly? Well, it's profits are going to be price times quantity, okay, and that's clearly going to be maximised to the price of a half. You know, remember this trick that has a 0 at 0 and a 0 at 1, so there must be halfway in between. So the maximum revenue they could possibly get in the second stage is a quarter. Okay. But if second stage revenue is at most a quarter, what are its overall profits? Well, overall profits are second stage revenue minus first stage costs. So quarter minus 3/4 Q1 bar. And as Q1 bar increases, this has to go negative. Okay, and the point it goes negative is Q1 bar becoming bigger than a third. Okay, so you know without solving the problem at all that firm I will never want to choose a quantity bigger than a third. Okay, and remember this was one of the assumptions we made when we solved the second stage game. Okay, we just assumed that both chosen a quantity less than a third. Okay, so we've proven now that they don't want to choose a quantity bigger than a third, so that's good. What quantity will they choose? Well, remember that in this second stage game, we showed they wanted to set price as this expression. Okay. So what are their total profits? Well, total profits are the profits they make in the production period, which are their price times the quantity they're going to sell, which is going to be their capacity constraint, minus the cost of investing in that capacity. Okay. And if you look at this expression, you know, hopefully it already looks like a two-firm Cournot expression. Okay, and if you solve that, I'm not going to do it now as we're a bit running out of time, but if you maximize this expression by choice of Q1, what you're going to get is, in a symmetric equilibrium, Q1 bar is Q2 bar is 1 over 12. And it's a simple exercise for you to go back to the original demand curve and solve for the Cournot competition outcome there. And again, you'll get the same quantities. Okay, so what's happening is that this quantity choice then price setting game is just equivalent to Cournot competition. So this is one way of thinking about Cournot competition. But firms are choosing capacities, and then at a later point in time, they're competing in prices. Okay, and the combination of those two things gets you something that looks a lot like Cournot competition. But this was all under the assumption of efficient rationing. Okay, so you can think of the key assumption behind Cournot competition. What drives Cournot competition is this efficient rationing. If you had a different type of rationing, you get a different outcome. And in particular, with proportional rationing, you get something that's much closer to perfect competition. Okay, so one explanation for those empirical results we had. Where was it? All the way back. Where was that? There. Yeah, one explanation for these results, that competition seems to be very close to perfect beyond 4 firms, is that it's not perfectly efficient rationing in the real world. The people who desire a good most aren't the ones who necessarily end up buying it. There's a bit of randomness to who ends up buying the good. Okay, and with that assumption, you get much closer to perfect competition. So really, Bertrand and Cournot, they're not alternatives. You can't really make sense of Cournot without really having this second stage pricing. Yeah, so this is quite a general result. You can always think of Cournot as this two-stage game, quantity then price setting. And the proof is far worse than anything I put you through today. Off equilibrium, the horrible mixed strategies to prove the Krebs-Schenkman result. So, I'm not going to flip that at you. But these guys, Davidson and Danekura, they look at other rationing rules closer to proportional rationing, and they show precisely what I said to get closer to a competitive outcome. So in summary of what we've seen, everything we've seen so far, as a social planner, you like price to be equal to marginal cost. Let's see when that's going to be true. Well, or no, let's see when it's not going to be true. Let's see when price is going to be bigger than marginal cost. Well, firstly, it's going to be true when firms have steeply increasing marginal cost schedules. It's going to be true when investing in new capacity is slow. You know, if investing in new capacity is slow, then it's likely to have this two-stage quantity then price game. It's going to be true when, it's going to be more true when consumers with the highest valuation ever want to end up buying the goods. Okay? And it's going to be more true when there are large differences in marginal cost across firms. You know, if there are large differences in costs across firms, then even Bertrand, the competition is indicating price equal to marginal cost. So really, you know, it's the rule rather than the exception, but price should be a lot bigger than marginal cost. Okay? You know, this perfect competition is this ideal, but there's no good reason to expect it to happen in reality. And here are some more exercises for calling competition. So linear demand curve, you know, this is the easiest demand curve you could possibly see, 1 minus P. So derive price and quantity, that shouldn't be too hard. How many firms enter, that's not too hard. Social welfare is a little bit trickier. Welfare optimal number of firms, a bit more tricky again. And then similar thing for quadratic. And then I also have some exercises about this kind of Krebs-Schenkman quantity then price. Okay, it's very similar, but with proportional rationing now rather than efficiency. With more exercises. Okay, so to conclude, we've got too little entry under Bertrand competition, too much entry under Cournot competition. And the way to think about Cournot is that it's capacity constrained Bertrand competition. Okay, and with tighter rationing that seems plausible, you'd expect the outcome to be closer to pricing for marginal cost than standard Cournot.